Okay, hi. This is going to be a couple of videos for your revision for class 336. This first one is going to be on chapter 18, part 1. So it's going to come in 2 parts, okay? So this is part 1. That's to keep it short, okay? So this is part 1. All right, so in part 1, we talk in chapter 18, we talk about how to represent cellular networks using LTI systems, or as LTI systems, I should say. Okay, and to do that, we start off with the system equation. So I'll do a bit of theory, okay, and then we'll go into some examples. So the system equation was this. So you have a set of state variables. So we'll have n equals the number of state variables. So these would be proteins or metabolites, whatever. And we have something called N and then also something called VP. So N is the stoichiometry matrix. That's the stoichiometry matrix. If we assume there's going to be R reactions, then the stoichiometry matrix will be an N by R matrix. The V is the rate vector, and you'll notice that that's a function of the state variables and potentially some inputs, which I'll designate P. The size of the rate vector is just R by 1, because that's the number of reactions. And of course, if you multiply these two together, you get the size of the dx by dt is obviously n by 1. Now, what we want to do, the rate vector itself is potentially nonlinear, and so we want to be able to linearize this in order to study it. So to linearize, I won't go through it, I'll just state what the linearization is. What we'll do is, though, we'll linearize around steady state. Okay, so linearize around steady state. So dx by dt equals 0. So if I do that, we get, this is something you might be familiar with. Oops, sorry. So it's the rate of change of the displacement times n dv by dx, dx plus n dv by dp, dp, okay? You'll notice that this has the same structure as an LTI system. This is the A matrix, this is the B matrix. The one thing I haven't said is how many inputs do we have? I'm going to use Q to indicate the number of inputs to the system. I also may use the word parameters as well, but this is the same thing. So we have a delta P there, delta X here. So that's the linear system. And what are these matrices here? So the dv by dx, that's an R by n matrix of partial derivatives. And the dv by dp is an R by Q matrix of partial derivatives. Okay, and if you only have one input, of course, the dv by dp is a column vector. Okay, so what I want to do now is I want to take this into the Laplace domain. And if I do that, let's switch to different color, shall we? If I switch to the Laplace domain, I get the transfer function, which is h of s, is si minus n dv by dx minus 1 n dv by dp. Oops, sorry. dv by dp. Okay, so that's the transform of the linearized equation. Okay, actually, let me make that a bit tidier. And notice we have an inverse as well. This piece is the A matrix, and this piece here is the B matrix. And so you'll realize it just looks like the thing we had before, minus A, minus 1, B, right? It's no difference. What about this matrix here? As I said, this is r by n. Okay, so it's an r by n. So it'll have the elements will be the individual derivatives. The top left-hand one is dv1 by dx1, and then because the r designates the rows here, because the rows times column, the v increments as we go down. So it's dv2 by dx1, dv3 by dx1, and so on, however many you've got. And then along the columns, we have dv1, we start incrementing the state variables. So that's dv1 dx2, then we have dv2 dx2, and so on. In the bottom right-hand corner, we end up with dvr by dx n. Okay, so that's the bottom corner there. Same thing applies to the dv by dp, and as I said before, this is an r by q. It's very similar. Okay, it's very similar. So for this one, the top is the dv1 by dp1, and that goes all the way down. The v's increment, keeping the p the same, and then on the columns, the p's increment, p2, and so on. dvb2, and then down at the bottom here we have dvr by dpq. Okay, so that's what we have. Oops, sorry. So that's what we have there. Oops. Okay, not a very good straight line. All right, so let's do an example then, okay, where we might use this to basically compute the transfer function. This is, I should have said, this is basically the transfer function, all right, of a cellular network. So let's have a little simple example. So let's do a simple example. I don't like this green. Let's try that one. So example, oops. Example. The example we're going to pick is a single gene that produces a protein X. That protein X degrades at a rate V2. The gene is controlled by a repressor, okay, which and the rate of production of protein X is at a rate V1. So let's write down what the various numbers are. So n, the number of state variables is 1. That's just X, okay? So there's only one state variable. The number of reactions is, let me put that back there. The number of reactions R is 2 because it's V1 and V2. And I haven't said anything about the input, but the input is going to be R, and there's only a single input, and that input only acts on V1. So Q equals 1. Okay, actually, didn't want that color. Q equals 1. So with that information, we can start constructing the various matrices. The stoichiometry matrix is a simple one. It's just 1 by 2. So it's 1 minus 1. Okay. The dv by dx matrix is, this will be a r by n. R is 2, n is 1. So it's a 2 by 1. So that's 2 rows, 1 column. And that gives us dv. I'll write them out fully at this point. And then dv v2 dx. There's no other state variable, so that ends there. And then the other thing we have is the dv by dp. This is an r by q. Q is also only 1, so we only have a vector there. Oops. So that's dv1 by dr. Now I'm going to immediately make a simplification here. R does not affect v2. Okay, so and this derivative here is dv2 dr. So that's actually 0. Okay, so that's actually 0. So now let's combine them together to form h of s. So here's h of s equals. Now, one thing we have to decide on is I. This term here, that's the identity matrix. The identity matrix, let me put that here. The identity matrix is n by n matrix, okay? And because n is just 1, the identity matrix is literally just the number 1, okay? Or if you want, you can put it in brackets if you want. Minus n, 1 minus 1 times this thing. Now, the dv by dx, let's make some simplifications here. So we know that x sorry, we know that x definitely affects v2. Okay, so x definitely affects v2, so that's non-zero. But I'm going to assume that x does not affect its own production, so that term is 0. So I end up with 0 and then dv2 dx. Okay, and I pull all the brackets around that, take to the -1, then another stoichiometry matrix, and then this vector here, the dv by dp, which is dv1 by dp 0. Okay, so now I just multiply this out. Don't forget this minus here, which is easy to forget. If you do that, let me write it out. Let me write out at least halfway anyway. So h of s equals s minus 0 minus dv2 minus dx bracket inverse of, and then it's dv1 dr. Okay. So this piece here comes from this multiplication, and this piece here comes from this multiplication. Okay. Obviously, this 0 here is redundant, and the two minuses, they cancel out to make a plus. Okay, so let's rewrite this. And then the inverse of a single scalar is just reciprocal. So we end up with this form. So we get 1 over s plus dv2 dx times dv1 over dr, and that's the transfer function. I can make some. Maybe I can say something about these v's, v1 and v2. Let's say v1 equals k1 times repressor and v2 is k2 times x. Then we know then that dv1, for example, dv1 dr must equal k1, and dv2 x must equal k2. Okay, I'm just differentiating these equations there. So now I can insert them back in, and I end up with k1 over s plus k2. Of course, we can immediately say, remember the characteristic equation? Characteristic equation. Actually, I don't like that. Let's write it out again. Characteristic equation is s plus k2 equals 0. So obviously, one root is minus k2, well, the only root. And that's negative, therefore it's stable. So this system is stable. Now you might also want to put this into a standard form, which it currently isn't. And you do that just by dividing top and bottom by k2. So k1 over k2 over 1 over k2 times s plus 1. That's the standard form. This thing here, of course, is the tau. Okay, and then this thing here is the gain. This is the time constant. All right, and there we have it. What about a bigger example? So another example, example 2. This time, let's have 2 genes. One produces X1, X1 degrades, also regulated by some kind of repressor. There's a second gene, which is regulated by X1. So you have this cascade of 2 genes, the first gene controlling the second gene. First thing, let's write down what the numbers are. So n, number of state variables is 2 because it's X1 and X2. R, number of reactions. Okay, there's one there, V1, V2, V3, do a proper 3, V3 and V4. So R is 4. Number of parameters, I'm going to make R the input, the only input. So R is 1. Do we need anything else? I think we're good. So let's write down the stoichiometry matrix for this. It's 1 minus 1, 0, 0, 0, 0, 1 minus 1. Okay. So this row here corresponds to X1. This row here corresponds to X2. Then we have V1, V2, V3, V4. Okay. The dV by dx matrix is a little bit more complicated. It's actually a 4 by 2. Okay, remember that was that's an R by n, and let's write this down. So the first one is going to be, let me just write down here, scratch pad here, dv1 by dx1. That's this one, that's this one here. I'm going to assume that x1 does not influence v1, so this equals 0. So I'm going to put a 0 here, okay? The next one is dv1 by dx2. What about that one? Let's see. Does x2 affect v1? No, it most certainly does not. It's way too far away. So that's also 0. So I'll put that to 0 as well. Okay. What's the next one? The next one is dv2 dx1. Does x1 affect v2? Does x1 affect v2? It definitely does. Yes, it definitely does. So that we definitely have this value here. Okay, what about the next one? Scratch that out. The next one is dv2 dx2. Does x2 affect v2? No, x2 is over here. It doesn't affect v2, so that's 0. So we put a 0 there. What about dv3 by dx1? Does 1 affect 3? Yes, it does. Okay, so 1 does affect 3 because it regulates 3. So that's definitely not 0. So that we have 1 there, v3, vx1. Now the next one, leave you figure this out, but the next one is also 0. And the next one is 0. The last one, which is dv4 dx2, is non-zero because x2 definitely does affect v4. So we have dv4 dx2. All right. So that's the dv by dx. What about the dv by the input matrix? Well, there's only one parameter, which is r, so it's just a single column. And r only affects v1. So in fact, we only have a single entry, non-zero entry here at the top, and then the rest of them are 0 because r doesn't affect v2, v3, or v4. So that's 0. Okay. So as before, I can multiply these things together. Let me turn that to orange. Okay, I can multiply these things together. Let me take you halfway through. So if I take the S function, this transfer function, it'll look like this. This time we have a 2 by 2 system. So the identity matrix is in fact a 2 by 2. And remember, we have to multiply by S. So let me do that here. So it's S00 S, okay, minus n times this. And n times this actually gives you another square matrix. Let me write that down. So it's minus dv2 dx1, 0, dv3 over dx1. There's a minus in front of that. Don't forget that. And there's a minus in front of that. We shouldn't forget that. Oops, sorry. No. I made a mistake there. There's a minus in front of this one, but not that one. And then this one is dv4 by dx2. And there's definitely a minus in front of that one. And of course, I have to take the inverse. And I have to multiply it by, remember, I have to multiply it by, I'll just show you again. Where is it? This piece here, oops. n times dv by dp. So let's do that. This is quite easy because there's only one element in the dv by t matrix, so that makes it easy. And in fact, it just turns out to be actually the same thing, in fact. Okay. All right. So now we need to invert the this matrix. So just to remind you, to invert a square 2 by 2, we invert a 2 by 2 matrix with these elements. It's actually 1 divided by the determinant, which is AD minus CB. Okay, and then we swap the main diagonal and we negate the off diagonal. Okay, and that's the inverse. All right. Okay, so the other thing we have to do is you have to, of course, this whole thing here, I should make sure make sure that's right. There's a whole another bracket across there, and that's the thing. That's the what's inverted. So we have to take this identity, this matrix here, which is a simple diagonal matrix, and subtract this from it. Now, if you do that, and then you do the inverse as well, you get this. And 0 there. This goes to minus v3. It's not a very good 3. dx1, and then it's s plus dv4 dx2. And then 1 over the denominator, and the denominator is the product of these two. Okay, it's the product of these two. So I've already done the swap, and I've negated the main diagonal, and so the denominator or the determinant is just the product of these two. And if I multiply those out, I get s squared plus dv1 dx1 plus dv what is that? dv4 dx2 plus dv2 dvx1 dv4 dvx2. So that goes all the way across. So that's the denominator. Of course, the characteristic equation for this system is this thing set equal to 0. Okay, and then the roots for that will give us the stability. Well, it's pretty easy to see what actually you don't even have to go that far. You just have to look at this. So the characteristic equation is just s plus dv2 dx1 times s plus dv4 dx2 equals 0. So that's the characteristic equation, because that's where the denominator, this is where the determinant comes from. And you immediately see that the two solutions, s1 is minus dv2 dx1, and the second solution is minus dv4 dx2. Since they're minus, the system is stable. Okay, also stable. All right. Okay, and that's as far as I want to go on this one. All right, so these are what the examples would look like. All right, you'd write down a network like this. You determine what all the values are for the components n, r, and q. You write down the various matrices, and then you substitute them into the transfer function expression, and then evaluate, and then you end up with a transfer function. And the thing you can get immediately from this then is the stability of the system. Okay, that'll do for this part. And I'll upload this, then I'll make part 2. Okay.